Hi everybody, Dr. Burns here. We're going to take a look at section 4.5, which is on the superposition principle. And we've actually been using this idea the last couple of sections, so this isn't an entirely new notion, but it kind of generalizes what we've been doing so we can look at a more broad way of solving these second-order differential equations. So make sure your cell phones are put away and you have your notes out and you're ready to go. So if we know that y1 is a solution to the differential equation, and that differential equation is equal to some function of the independent variable, and we also know that y2 is a solution to the same differential equation but equal to some other function of the independent variable, then for any two constants, k1 and k2, or c1 and c2, doesn't matter what we call them, we know that the combination, the linear combination of k1 y1 plus k2 y2 is going to be a solution to the differential equation. ay double prime plus by prime plus cy equals to k1 times f1 of t plus k2 times f sub 2 of t. So how can we put this together and use this to help us find particular solution? Let's look at a couple of examples here. Suppose we are told that y1 is a particular solution to this differential equation. Notice that this is equal to 3t, and y2 is a particular solution to the same differential equation but equal to the function 10e to the 3t. So they want you to use this information to find a particular solution if we know that the same differential equation is equal to negative 9t plus 20e to the 3t. So what you want to observe here is that this expression on the right side of the differential equation they want us to work with is basically a linear combination of these two functions that we started with, the 3t and the 10e to the 3t. So specifically, let's kind of write that out. This expression right here, negative 9t plus 20e to the 3t, is equal to negative 3 times 3t plus 2 times 10e to the 3t. I'm never leave myself enough room here. Let me clean this up a little bit. Here we go. Let me write that again. 10e to the 3t. So in other words, this is a linear combination of these two solutions right here. So essentially what you have is a k1 of negative 3 and a k2 value, a constant multiple of 2. So our particular solution, y sub p, is going to be equal to negative 3 times the first solution, that's y1, so 3t over 2 minus 9 over 4, plus 2 times that second solution, 10e to the 3t. And that's it. That's a particular solution then to the differential equation they asked us about that was a linear combination of the two that we started with. And that's really the superposition principle in action, just combining those two solutions. Let's do another example. So this one says, given that y sub p is a particular solution to the differential equation, they want us to find a general solution knowing that y of 0 equals 1 and y prime of 0 equals 0. So this is basically an initial value problem where they give us one particular solution. So remember we said previously that a general solution, y of t, could be expressed as what we call the complementary solution plus the particular solution. And that's what we've been using in the previous two sections. That's really the superposition principle. So what I'm going to do is I'm going to go ahead and find a complementary solution to go with the particular solution that they've already given me of t squared. So let's go back and let's remember how to solve a homogeneous second order equation using the auxiliary equation. So note that we've got y double prime minus y is, if we set that equal to 0, our auxiliary equation becomes r squared minus 1. So set that equal to 0, r squared equals 1, and my solutions to that auxiliary equation are plus and minus 1. Those are two distinct solutions, and so that means that my complementary solution, y sub c, is going to be C1 e to the t, because r is positive 1, plus C2 e to the negative t, because r is also equal to negative 1. So if we put these together, then my general solution is going to take on the form C1 e to the t plus C2 e to the negative t plus the particular solution that they gave me of t squared. So that's going to be my general solution. Now let's use the initial condition information they told us. They told us that y of 0 is equal to 1. So we know that the original function is going to contain the point 0, 1. So if we substitute that in to the general solution, we wind up with y equals C1 e to the 0 plus C2 e to the 0 plus t squared, of course, is 0. So that means y equals C1 plus C2 is one equation. Now let's go ahead and find the derivative, and then we can use the second piece of information they gave us, a second initial condition. So we know that y prime is going to be C1 e to the t minus C2 e to the negative t plus 2t. And then they told us for the derivative that it goes through the point 0, 0. So if we substitute 0, 0 in to that equation, we end up with C1 e to the 0 minus C2 e to the 0 plus 2 times 0. So we have 0 equals C1 minus C2. So what I want you to notice is you've basically got a little system of equations where you can solve for C1 and C2 using that information. We know then that from this equation, C1 must equal C2, so if the two of those have to be the same, that means that in this equation, they both have to be 1/2. So C1 and C2 are both going to end up being 1/2, and then my general solution is now going to look like a particular solution of 1/2 e to the t plus 1/2 e to the negative t plus t squared. And that is going to be the solution that they were looking for that passed through the points they gave us. So that's it for this lesson. Make sure you bring your notes with you to class tomorrow, and we'll do plenty of practice.